Okay, I've started the recording just so everyone knows, and I think we're going to get started. This is going to be a pretty informal talk. I've just decided to put this together because I've got a lot of questions on the Slack discussion about how we do things, and I figured it'd be easier to kind of just go through everything with some slides. But if anyone has any questions, I feel free to jump in, either ask on the chat or just ask at the mic. So, hi, I'm Nick Banks from Microsoft, one of the main developers on MsQuic, and I'm just going to give you kind of some overview on performance-related designs that we have for MsQuic. Just real quick, we can go through kind of high level on the overview and constraints we have for the library, and then some of the design. We'll walk through a little bit of the code, and I'll give you some more information on how we do our testing and tooling. So at a high level, MsQuic is just meant to be a general purpose QUIC client and server implementation. It's not HTTP specific. We've got a lot of other products at Microsoft that are already using it or have plans to use it. So we've got a lot of different scenarios that we need to satisfy. Like it says here, primary ones were definitely HTTP and SMB for us to start, but more things, even things outside of Windows, have pushed us to support Windows and Linux, looking at other platforms as well, and then all sorts of application spaces being looked at and investigated. And obviously performance is a big goal for all of those. So right off the bat, we were looking at a performant design as a primary goal. So along with that came some constraints. One of the big requirements for us is that it had to run in the Windows 10 kernel. That the reason for that is several of our clients, being HTTP and SMB, are Windows kernel components. So for them to call us, we had to be in the kernel as well. Being in the kernel comes with a couple of requirements. Generally, C programming language is required. It does support some C++, but not really enough, in our opinion, to warrant using it. The kernel uses asynchronous network IO model. I'm down there in the kernel, pretty much you call down into the stack, and it's going to end up directly calling into the NIC, and vice versa. When they indicate a receive, you're going to be in that call stack. So that is one point that really drove our design for the data path. Then we've got kind of two primary scenarios initially. HTTP, which was more primarily focused on RPS and latency. So they wanted to get lots of requests, want them very quickly with minimal delays, while SMB is more focused on the bulk throughput. They want the single or very few connections as fast as possible. And then after that, we started getting more customers, more people coming on. .NET Core is probably the next really big one, and their big desire is cross-platform support. They're also initially in the HTTP space, but they'll eventually expose the transport as just a native transport to allow native QUIC apps. So bottom line though, we have all these kind of constraints and requirements, but pretty much our number 2 goal after only functionality is performance with MsQuic. So I'm going to jump into the design here at a very high level. So MsQuic itself is the center orangish-brown part here, and it's split into two main parts. You've got the core protocol logic, which is platform independent. So the goal there is there should be no code that says if Windows, if Linux, or anything like that. That is your primary logic that is common to everything. Below that is the platform abstraction layer. So that's the part where you get the different implementations for each platform, whether Windows, Linux, Android, Mac. Those sit in that abstraction layer. One big point is we try to inline as much as that is possible. So we have essentially one really big header file for each platform that has most or a lot of what we need inline. So things like threads, locks, interlocked operations, all those are just inline in the header file, whereas the bigger things like the data path, essentially the socket abstractions, have to be in their own file. They're just a static library. So this is mostly going to talk about the data path parts of that, though. So as I mentioned before, the Windows kernel kind of drives the asynchronous I/O requirement for the data path. Just to be clear, if people don't quite understand what that means, I mean, that's just you are calling and there are essentially a lot of up calls on the receive path, and then on the down path it will be sending and queuing where necessary and returning asynchronous completions and running inline where possible as well. So it's just a lot of event-based, callback-based data path, which is not what a lot of people, at least outside of Windows, are used to when you're talking about normal, say, blocking or non-blocking sockets. So, like I say here, in receive calls, you get your up call. The lower layer owns the buffer. They give you a buffer. We generally support either handling that buffer inline and returning success, or you can return pending and essentially have another down call at a later time to give back that buffer that you pended. And pretty important part, we'll talk a little bit more, is you have batching in both directions. So when you're really trying to optimize the networking stack, especially at the UDP layer, there's only so many kind of cycles per byte you can squeeze out of sending a single packet down through the many layers, especially on Windows, which has got a lot of legacy components in the stack that need to be traversed for every single packet. So pretty much the primary way to speed that up without skipping all the kernel and talking directly to the NIC is to batch. Instead of sending one packet through that kind of gauntlet, you send a lot of packets all at once. And most of the processing is only going to happen on the metadata of that. Most of those packets all having the same metadata, same source and destination IP address, stuff like that. They only have to pay that cost once for the whole batch, where it's essentially the same cost as if you were sending just one. So another really important part of our design that is fairly different, what I gather from a lot of implementations out there, is our threading model. We own all the threads for all of the execution of the QUIC logic and below. So at the data path layer, there are threads. In user mode, there are user mode threads that are essentially draining the sockets, indicating the data up. In kernel mode, we get the callbacks straight from the NIC. So in kernel mode, the NIC driver is going to indicate receive packet. It's going to go up through the TCP/IP stack, go through UDP, and then eventually result in a direct upcall to our QUIC abstraction layer. We'll do some processing, and then that's going to be a direct call straight to the core logic. So, and as I mentioned on user mode, obviously you can't get direct upcalls from the networking stack, so you have your own threads that are draining the sockets, essentially posting receives, waiting for them to be completed, and then when they're completed, indicate that upcall into the core thread, and then once it returns, essentially goes back and starts draining the next socket again. So on that thread, the core logic does a minimal amount of work. Its main goal is to take those packets it receives from the UDP layer, find an appropriate connection for them, queue those packets on the connection, and return. In the case of the server side, obviously that means it needs to be able to create new connections as necessary, so that logic lives there as well. And once you queue the packet onto the connection, essentially you kick the connections worker thread, and then that's where really the bulk of the work is going to happen in the core threads of MsQuic. So these are the threads that will essentially process their connections, run all the work for all these connections, and that's where we do upcalls to the app. That's where we build packets that need to be sent out. All the encryption and decryption happens on those threads. Going back to the callback threads from the data path, because those are happening straight from the NIC, they're generally happening at a much higher interrupt layer than the rest of the operating system. And pretty much bad things happen if you block those threads too long. And you don't want your mouse or your audio glitching because you decided to try to decrypt a ton of packets at that dispatch level. So that's why we do minimal amount of work, pretty much some lookups, some allocations in the case of needing to create new connections, and then it's all queued to the core worker threads. And that's where everything runs at the normal interrupt levels, the rest of the OS, and everything runs without impacting the system. And then on top of that, obviously, generally you're going to have app threads. The application is allowed to do minimal amount of work. Again, kind of the same thing as core on top of data path. You can do a minimal amount of work on the callback thread, but anything of real consistent worth is going to happen on. Is there a question? Okay. All right. One more level here is how this interacts with what's called RSS, or receive side scaling. So we take those threads, that essentially that same threading model, and then it's multiplied for every single processor on the system. I mean, we have a cap. Currently it's at 64, but that's just a hard-coded. But the bottom line here is, at least generally on server systems, the network drivers indicate packets according to this RSS, which pretty much comes down to a hash of the IP tuple based off of a secret that allows it to consistently indicate those packets only on a given core. So what that means is, for a given UDP 4 tuple, those packets will always be received, say, on core 10. So if you have that assumption from the lower layers that the packets are always going to arrive on a particular core, you want to try to keep all the work for processing those packets on that same core. You don't want to have the memory for the packet itself, the memory for the connection objects, or any other objects at the higher level having to jump around between cores as you're receiving more packets. Worst case, if say you're jumping across different NUMA nodes, then I've seen like our high performance tests, high throughput bulk throughput tests drop as much as by half just because of not consistently staying on one NUMA node. Robin asked, does this design of encoding core info in the SID mean it's more difficult to use this implementation in proxies, for example? I'm not necessarily. I don't expect the proxies to be involved in the SID, the connection ID manipulation. Robin, you want to clarify like why you think that would be a problem? Because with any implementation, the SID that a endpoint gives out to its peer, the SID's a black box. Unless you are a cooperating middle box, say like the load balancer, the SID itself shouldn't be used or can't be used really by those other devices, other middle boxes. Does that answer your question, Robin? Do you have more? Feel free to come to the mic. I can see you, I don't hear anything. I can see you. I can't hear you. Pretty much, the proxies aren't going to have any insight into this. The hashing is purely a function between the server's network card and the server's OS, at least for Windows. So the only thing the proxy really has control of is that IP tuple. And as long as the IP tuple between the proxy and the backend server is consistent, the hash will stay consistent. As I mentioned here, though, we do have the ability to adapt to changes. Obviously, QUIC is fundamentally designed as a protocol to allow for changes in the IP tuple. So we can't just say, hey, we're going to keep one SID that encodes a particular processor, essentially particular core, and it's never going to change. So one thing that I helped kind of drive into the spec itself is the ability to retire existing connection IDs and then create new ones. One of the main reasons for that, at least from our perspective, is to support changes for this. And obviously, there are several reasons why that might happen. Obviously, the tuple itself can change. RSS itself supports the ability to theoretically dynamically rehash, to reshuffle, and if that happens, you'd need to regenerate this. But bottom line, any case where the essentially primary core of that connection needs to change, then you need to regenerate the SIDs. And all that works, and the idea of encoding the essentially the partition ID is what we call it into the SID itself is also just an optimization. So what that means is if the client unexpectedly changes IP addresses, I can say NAT rebinding, and now all the packets start coming on a different core, that server ID that's encoded in the connection ID is now going to result in an inefficient lookup because there's going to be cross-processor access, but it's not going to fail. So there'll be some time until we are able to essentially flush those new connections out or flush those new connection IDs through, send them out, get the response. And during that time, we'll have some inefficiencies with that. But once we get the stuff essentially all worked out, then the things go back to normal and they're more performant. So yeah, I'm pretty much, the proxy doesn't need to change the SID. So you're saying like, okay, what if the front end connection, the client changes IP addresses to the proxy? As long as the tuple between the proxy and the server is not changing, there's really no need to change the SIDs. So if there's a proxy, it's got to handle IP changes from its client. But if there's no IP change between the proxy and the server, there's no need to change connection IDs. Yes, generally. But if the proxy for some reason changed, it's not any different from the server's perspective than any other client IP change. So I think bottom line, you just have to see each connection, server to proxy and proxy to client, as completely independent. If there are IP changes on either side, they're reacted to accordingly, but they shouldn't affect either other connection as far as encoding that information. Because that's the whole thing. Those connection IDs encode information specific for just that connection. And that that other connection is still a different independent connection. It might be seen as at a higher layer as a different connection, but it's still a different independent QUIC connection. And if you were trying to somehow proxy UDP, yeah, I don't think you need to worry about that. You should be able to see them as independent. Thanks for the questions, Robin. Any other questions or comments on RSS? I think I covered everything here, answering Robin's questions. But really, kind of the high level to take away is QUIC has its own threads. It does not let the application kind of drive its own threads. This is definitely a different model than a number of the QUIC libraries out there. This puts a lot of burden on kind of the app to handle these upcalls. Some applications, especially if they're being ported from normal sockets, won't have this logic built in, so this would be a change for them. It can create a lot more threads, but in our experience, it's very hard to get kind of all this stuff set up just right to be highly performant, especially when you're trying to take things like RSS into account. And from our point of view, it's easier and kind of better for the overall ecosystem for us to do all the work up front to try to manage all these, to have a highly parallelized, kind of partitioned, independent worker segments here to get as much kind of efficiency in the system as possible. All right, so after this, I'm going, okay, there's one more. These are kind of just good to know, good things to do in practice. As I mentioned before, batching is extremely important on the data path, but I'm pretty much batching in anything you can do will improve performance. Send and receive path. This is talking really from the app to QUIC and from QUIC to UDP. You want to be able to support batching wherever possible. So our application API, an app can call send, and it can provide us variable number of buffers that it wants to send all at once. What this means is it can be easier for, say, HTTP that wants to frame a request. They don't necessarily have to allocate it all in one contiguous buffer. They can do one send that's got part of the buffer has headers, then another buffer for contents, anything else. They can buffer multiple things in different applications. For instance, SMB is how it's currently set up, uses generally only one stream, but it has messages. in chunks. They can theoretically send multiple of those chunks in one if they wanted to. But bottom line, you want to support this batching because definitely once you get down to the UDP layer, batching is extremely important. That's really the difference of doing maybe a gigabit throughput on your bulk versus multi-gigabits and higher, and especially once you have network card offload for that thing. That's where you really start to see your improvement. Same thing on the receive side. Our abstraction layer between the data path and QUIC is a receive that we indicate essentially a list of packets up. And from QUIC to the app, we give them, it's an array, but it's a set of buffers up, which again can make things more complicated because you have to handle these scenarios where sometimes you have one, or maybe most of the time you have one, but sometimes you have more. But it allows you to improve the efficiency and get the extra cycles per byte and improve your throughput. Encryption and decryption, we haven't quite gotten any kind of batching for payload encryption and decryption, but we do have batching for header protection. So I'm trying to remember the numbers, and because we did this over a year ago, but before batching header protection on our high throughput performance, I think you do an overall CPU usage of throughput, and header protection could be anywhere between, I don't know, 3 and 5% of total CPU usage. And for something where you're only encrypting and decrypting a couple bytes, like it totally seemed extremely wasteful as far as CPU usage. And initially, because of that, there was a lot of pushback on should we even do this because it hurts throughput by as much as 5%. But when you batch that, you can make that go away almost entirely. So we support batching in essentially batch sizes of 8, I believe, and effectively the CPU time it takes to batch, encrypt, or decrypt 8 packets is pretty much equivalent to the time it takes to do 1. So you take that 3 to 5% and you divide it by 8, and it definitely improved things there. Essentially made it fall off the kind of hot path for the most part. So now you're talking 0.5% of total CPU usage. So yeah, thanks, Dimitri. Dimitri commented that they borrowed the same technique and implemented in MsQuic, and can confirm that there were performance wins by doing that. Thanks. ACK processing, pretty much anywhere you can do batching, it can definitely speed things up. I mean, a lot of times, even if it's as simple as like memory locality, accessing the same stuff over and over very quickly, it definitely makes things better. And then really the only high-level things I can recommend have to do with like memory allocations. If you're going to have some memory that you use a lot, even if it's kind of like a temporary working memory, we pre-allocate that kind of stuff and keep it allocated and associated with the connection, if not even allocated as a part of the connection. One such instance for us is we have a working set memory for processing ACK blocks. I'm trying to remember how much we pre-allocate. I don't think it's a huge amount, but we have this memory that we pre-allocate, and every ACK we receive, we essentially decode it into that memory. We flip it around because we want to process ACKs from oldest to newest instead of the order that they're encoded, which is newest to oldest. And I have that in the code walkthrough and explain why. But we have that memory always allocated on the connection and just keep it around. So Yucheng asked, the QUIC decrypt function takes quite high CPU usage, up to 20%. I've seen it take up as much as 75% of the total CPU usage. You're asking, is the performance after using batching? So this is the flame graph I have in the slides. I'll go through some more, and I'll have a walkthrough actually using WPA itself. But this is for batching of header protection. We don't have batching for the actual payload protection. So there's no batching at the kind of the bulk QUIC payload. So that really is one area, or kind of, it's obviously the biggest area of CPU usage. Like I said, we'll get to that more later, but there's not a lot you can do there. Batching is more difficult for a couple reasons there. One, they use completely separate, I believe it's IVs. So you have to generate new key material for each individual packet. You can't use the same material like you can for the header protection. They all use the same stuff. So because of that, you can't batch the same way as header protection. And also because they're so big, the CPU usage really comes from generating the key material, not so much as, I mean, obviously decrypting itself, but you can't really get any, or you won't really be able to get much batching improvement there. We want to play around with it some, but it's not really clear how much improvement we can get there. And Robin also pointed out, if it's not clear, Yucheng, there are two separate decryption steps. Yeah, one for the header and one for the payload. What we have currently is just for the payload. Sorry, what we have right now is just for the header, and the QUIC decrypt function is what we have. What's showing up in the flame graph is for the payload, and that's not batched. Hope that answers your question. Yep, no problem. Going back to the allocations, like I said, pre-allocate what you can, and then for things that do get generally allocated on the data path, well, really anywhere, but we use pool allocations. The pool allocator is practically just a small wrapper on top of any normal allocator that has a linked list that is really a most recently used queue of allocations. So when you call alloc on the pool allocator, if it's got anything in its queue, its cache, it's going to return that to you immediately. If it doesn't have anything in there, it'll go down to the allocator and actually allocate the fixed size object. And then on the free side, as long as the queue hasn't hit, the cache hasn't hit a maximum size, I can't remember what we have currently, it might be 128 or 256 items in the pool, it's going to just put it in the linked list and essentially push it on top, so the next alloc that comes along just pops it off. So what this means is once you hit your steady state of allocations, like the steady state where you're generally allocating and freeing the same number, or really the same, say, UDP packet buffers over and over, then you're not really allocating, at least as far as the allocator is concerned, in that code path. So you're just end up doing what we have, at least on Windows, is, I think on Linux we use a lot, but on Windows we have an interlocked operation to pop that off the list and get the next one. So it makes it very efficient, and then practically when you look at the CPU usage, allocations are nowhere to be found. So all you're doing is real logic. So this gets rid of those, and like I said, we use these all over the place. Anything that has a fixed size object, essentially any structs, any anything that's a struct, anything that has memory that is of a fixed size, like packet buffers, we always allocate them of a fixed size for doing sends or receives. Those are using those pool allocators, or they're also called look-aside lists. I'm not sure how much these are used outside of kernel code, but I'm at least from my experience, these are really common inside kernel, at least network drivers definitely, not so much outside, but definitely makes a difference as far as improving performance. Okay, so now I'm going to go through some of the code. So this, I can go in any level of detail of this code. I can like breeze through these functions real quick, or I can go in more detail. Do anyone have preference in here? And we've got lots of time. There'll also be lots of time for questions and discussion at the end. I've had lots of people ask for how we do things. Some of this, it really gets down to looking at the code. Anyone have any preference? Otherwise, I'll just kind of go through it fairly quickly. Okay, silence. So let's get started. So we're going to start with the UDP Receive, and specifically we're going to start at the QUIC layer. Essentially, I'm not going to go through any platform-specific code today. So this function, QUIC binding receive, binding here just standing for UDP binding, essentially some tuple binding. This is the upcall that we receive from the platform-specific code on on Windows kernel. This is going to be directly in the call path from the network card. In user mode code, it's just running on a socket or on a thread that the data path is essentially driving the receive code paths for. So I'm not going to go through in super detail, but the kind of main thing to note here is we have a chain of packets. These just have next pointers. So these are just structs that represent our packets that have all the necessary information like tuple, ECN information for it. So this abstracts essentially a whole UDP datagram, and there's a chain of them. So there could be one here, there could be 64 here, or 128. The code here does not care. So the goal for this code is we received a chain of packets on a binding. It doesn't necessarily mean all of the packets are for the same connection, though. It's theoretically possible that the network card coalesced them, especially if you're talking about server side, where you just have a listening socket that's saying, maybe it's just listening on wildcard address, and you just received a batch of a ton of different packets that aren't quite matching up. So the first step here is to try to go through each packet and break it up into sub-chains that are all matching. So this does some validation of the packet. Might remember I said we do as minimal amount of work on this thread as possible, but to be able to find which connection this packet is assigned to, we do need to do things like process the header of the packet. See, we're going to go here, we validate the invariant part of the packet, check if it's a supported version, whether or not we have to generate like a stateless reset or version negotiation. There's a lot of validation, a lot of kind of nitty-gritty details of a QUIC library itself. And Dimitri asks, is breaking it into subchains done for performance reasons? No. So the goal here is really to deliver it to the correct connection. So breaking it into subchains is just trying to get it's trying to get the largest unit that would go to a single connection. I guess, are you asking is breaking it into subchains done as opposed to breaking it into individual packets for performance reasons? If that's what you're asking, then yes. So like if we receive 64 packets and say 32 of them are really destined for one connection and 32 are for another, yes, we want to split those into 2 chunks of 32 and essentially make 2 queue calls on each connection instead of 32 queue calls on each connection. So, okay, yeah, so that is what that makes sense now. Yeah, I understand your question now. So yes, we're trying to break this up into as large of chunks as possible, but the chunk still needs to apply to only a single connection. So we do some validation. We've got some tests. This is essentially test-specific code for doing some validation. We break it up. We have to do some logic to essentially say, does this match the current subchain? If it does, we'll continue on and add it. If it doesn't, we essentially deliver the current subchain to the datagram. And we've got some logic here to try to put handshake packets at the beginning of the chain. This handles cases where you get packets possibly reordered. Generally, it's not really a big deal, but this is just so we have long header packets kind of at the beginning. And then at the end, whatever the last chain is, we deliver it, and then we return the chain back if we have anything. So as far as delivery of packets goes, lots of text, lots of comments. We're essentially, we have to, once we have the chain, we can essentially take the first packet that we grab from that chain, and then we have to find which connection. So we have 2 lookup modes for connections. One for essentially short header packets and sockets owned by a client. And I'm not going to go into all the details, but essentially you can just use the destination SID directly. And this is where we're going to decode the partition ID to try to find the right lookup table fast. And this lookup table is actually generally an array of tables, 1 table for each core. So ideally, only a single core is ever accessing its table. So while there are locks, it does work if there's cross-processor interaction there. It's generally very efficient in the case where you have lots of connections, but each connection is respecting RSS and everyone's staying on the same core. In the case of server side, where you have your initial packets that aren't using the server's destination connection ID, we actually look up by hashing the source SID and the remote tuple. And there's a lot of reasons for that. I'm not going to go into too much of the detail, but bottom line, when we do a lookup, we try to find the connection. If you don't find the connection, we've got logic to essentially say, hey, should we send a stateless reset? Is this server? Is it appropriate versioning? And then is this an initial packet on the server? I mean, lots of stuff to essentially come down to say, hey, should we create a connection in response to this? So eventually, whether we create a connection or we find the connection and look up or do something else, but if we result in having a connection, we then just say, queue the packets onto the connection, and then this thread releases its reference on the connection, and we're done. And queuing the packets is fairly trivial. Might not look at first glance, but we do some logic here to count how many connections are, and what you probably notice, this is one of the very first places we've had a lock. There was a lock on the lookup, but we try to reduce the number of total locks as much as possible. But pretty much you lock the queue, you add the chain to the tail of the queue, you unlock the queue. That was the extent of all the lock on there. And then all work, like I've mentioned before, for a connection really runs on the core worker thread, which we'll get to that in a little bit. But we have this notion of operations. So we essentially queue this operation, flush receive, onto the connection, and then this guy's done. He falls back, jumps out, and that's the end of quick binding receive. So that's essentially the UDP receive path. It's all about do some pre-process on the packet, find the connection the packet's for, queue the packet on the connection, do that for all packets, all datagrams, and then break out. And that's pretty much all the UDP threads are doing. So the UDP thread is just doing that on all cores. On kernel, it's directly on the kernel threads. In user mode, it's in the user mode threads. But what this gives you is the ability for those threads to be parallelized with the QUIC worker threads. And especially in the, like I said, in both kernel and user mode, but the CPU cost it takes for a packet to go through the whole like IP, UDP, and this part of QUIC receive path is insignificant. So this allows you to parallelize essentially all that receive code with the QUIC's processing, and then the send path happens on the QUIC thread on its code, on its thread. So say for just a single connection high throughput, what that means is one core can end up doing the receive code path, and one core can end up doing most of the send, and you get a good bit of parallelization there, and some CPU wins. I mean, depending if it's mostly a sender or receiver, obviously one of those is going to far outweigh the other. So I mean, obviously a primarily sender is going to have a lot more CPU usage attributed to send, a receiver on the receive. Any questions there before I go to I think, yeah, the QUICs and the QUIC receive path next. Okay, so here's the QUIC side of things. This is what's going to be running on the QUIC worker thread. So what it does is it locks that same queue that we just saw a minute ago, and it grabs all the datagrams off the queue and then unlocks it and continues on. So this is where, again, I have stressed batching. So we're grabbing the entire queue. There might be, I don't know, there might be 5, there might be 105 datagrams that have been queued on this by the time the connection finally runs to flush. And obviously it's highly dependent on scheduling scenarios and how many connections there are, how fast you're receiving packets, stuff like that. But you grab the whole queue, and then we just process the whole queue at once. And this is going to go through and practically go through each datagram, and we do some processing. So this batching is where we're going to do, yeah, so the batching here has to do with, we batch mostly the header protection. So you'll see we've got essentially this memory we allocate on the stack that is having to do with batching the header protection samples. And how you batch header protection is pretty much you have to copy all the headers into one contiguous buffer, and then you call into the crypto API to decrypt all at once. So there's this code is even more complex than it would normally be, but a lot of that is because of the batching. Batching makes you end up having to have a couple places where you say, okay, is this where we need to process the batch because it's different from the last one? Because you can process long headers and short headers, and those result in different kind of batching logic. Or have we reached our batch count? So batching gives you a performance win, it is not a win on the complexity side. So you're definitely paying a cost by adding these kind of features to squeeze more CPU usage out of the system, but paying that cost in complexity. So, like I said, you go through this batch is where you eventually process things, your computing headers. We essentially get ready to decrypt. Essentially, again, it's a lot of it's packet validation. We decrypt it. We process the frames. We do some post-processing. A lot of this is related to migration, things about changing if the IP addresses change. You need to regenerate the connection IDs. So I don't think it's quite worth going into all the details of this. And this starts to get down into kind of a standard QUIC implementation, processing frames, doing all that. But this is essentially at this point we've gotten rid of batching. We don't have any more batching. This is where we're doing for each batch. A lot of stuff for do we need to update partition IDs? As you can see, it's non-trivial logic to keep all those connection IDs in sync with possible changes from the lower layer being on different threads and stuff. Any questions about the receive, the connection side of the receive code path? Or preferences for me to go in more detail? I don't know how much everyone wants to see, like the exact inner workings of this. All right. Okay, Robin had a comment. Said, to be able to do the batching, do you need to copy the headers together so they're contiguous? Yes. So generally, I just go into one of these batch calls so you can see what we do here is we call into the platform specific to compute the header mask for this. So these functions operate on contiguous buffers generally, because this is really just going to result in an encrypt call. So you can see when we call compute header or header protection compute mask, it's just going to result in an encrypt call on one contiguous buffer. So we need to copy into that one buffer because the lower level crypto APIs only operate on contiguous buffers. So to get this batching, essentially to be able to have this one call do all 8 packets, you need that contiguous buffer. So that's why you pay a little cost in copying. But again, we're talking about, well, because we only do batching on short headers. So you're talking about less than 6 bytes, right? Or like very small sizes, or I guess this is for the cipher size. So you're talking about 16 bytes that you have to copy per packet. It's not a lot, and the wins were pretty clear when you look at the flame graphs afterwards. So, but yes, you do have to copy them. All right, let's look at the send path. So one other thing that is not, I didn't talk about on the receive path real quick, is you process this whole batch of packets. We do not send an ACK until the whole batch has been processed. So we don't do any kind of after X packets force an ACK to be sent right now. From our experimentation, we've gotten really good results of essentially just dynamically ACKing essentially whatever batch size resulted from CPU execution. What that means is as you're receiving faster and faster and batch sizes possibly increase, bigger and bigger, you end up having those larger sizes, essentially those larger numbers of packets getting ACKed all at once. So just to say that another way, our ACK sizes, essentially the size of our ACK frames or the number of packets we ACK at a time, ends up being essentially our receive batch size. So as we receive those packets, we're processing each packet saying, okay, this is a good one, it needs to be acknowledged. This is a good one, it needs to be acknowledged. We're building up those packet numbers that need to be acknowledged. Once the whole flush receive operation is done, then the flush send operation goes. So flush send essentially operates on kind of some metadata that says, hey, these are all the things that need to be sent right now. So kind of at a high level, we have all these different send flags that we keep track of. Oh, okay, we need to send ACKs or crypto, connection close, application close. These are connection-wide, essentially control messages that we need to send. And then we also have ones at the stream level saying, okay, we have a list of streams that might need to be sent, and then on each stream we have some metadata saying, okay, these are all the things that need to be sent on that stream. And the goal of the send flush function is just to operate on all those metadata. It has the essentially logic to say, okay, given the current state of what flags are queued up to being that need to be sent, go through, build up all the packets, put the frames in those packets in the appropriate order, because there is some priority order, at least for QUIC, as to what order you frame frames into QUIC packets. And that's the goal of this. So we have this kind of packet builder struct that's just a helper for picking like what type of packet, like long header, short header, building up some of that header, and then at the end, essentially doing the encryption and finalizing stuff. So this is kind of our helper for that. So we create that. There are a lot of things to take into account when you're building packets. You've got an allowance, which has to do with generally amplification protection. Your amplification protection essentially states that until you validated the peer's IP address, you can only send up to 3 times what you've received. So this allowance is that where we apply that 3x validation. When we validate it, this just gets set to UNT32 max. So it would always pass this check. Stuff having to do with keys and a lot of other logic. Congestion control has to apply. Pacing gets involved at this layer. But bottom line, the meat of all this is then sending packets, building packets. So how our kind of priority goes is we always send out connection-wide control frames first. Then we build up stream frames and any stream metadata, and then essentially on the stream itself, it will send stream control frames before it sends data frames. And then got some logic on this. Kind of has to do with prioritization. When you're done with a stream, if it still has more data, do you put it back at the front of the list or at the end of the list? I know Robin has had questions on like what if you have a more complicated prioritization scheme. If say each stream had a priority ID or a number to it, putting it back into the list would just essentially add a bit of complexity back here. And then finally, we've got some logic for sending PMTUD discovery packets. It's a little special because that means we end up allocating packets bigger than the normal ones. And again, you have to do some special logic. And then eventually we're going to break out. And again, this finalizes more batching stuff. Essentially, remember, Just like we batch header protection on the receive side, we do it on the send side. So you have a similar kind of logic where this finalize is really finalizing the current batch, finishing the header protection, and then sending it off. I'll go down into some of the details there. And we're just sitting in this loop, constantly sending a new packet or building a new packet until we're finally done, or we have some cap for how many packets we're willing to send at a time, just to allow for kind of sharing between multiple connections on the same worker, and then we clean up and we bail out, and we might reschedule the send if we didn't actually finish sending. But trying to think, for these, not prepared. For sending, it's all about, we have the metadata and we're going through, okay, is connection closed, queued to send, okay, build up the close frame. Path response need to be sent. Handshake done. So these are pretty, again, straightforward things for any QUIC implementation. They have to keep track of what needs to be sent, and then you've got your fairly straightforward code for building up your frames into the buffer. This is data blocks. I'm building up. This just the kind of the really low level stuff of this is how big a frame is. This is make sure you have enough buffer to put the data for the frame into the buffer, and then actually do it. Return true or false if it works. And kind of a important thing here is on this builder we have metadata, and I know I've talked with at least Robin about this. This metadata keeps track of all those all the frames, all the flags that are being sent for the packet. So whenever you send these packets, you're going to have to keep track of which packets are currently outstanding. So that go into one of these finalize functions. So when you finally send out your batch packets, you have to then keep track of that metadata. So we have a component, is loss detection, which I'll go into next, at least on the receive side. Sorry, there's a lot of code here. So we have this loss detection packet sent. So this is where we pass in this metadata struct, which holds how big the packet was, which path it was sent on, what frames were in it, what streams were in it, how long the stream data was, what the offset was. Essentially, everything we would need to reconstruct that packet. We don't save the actual packet. So that's one thing to be clear. We don't save the packet itself. We don't want to save, especially if you're talking about at 5 or 6 gigabit throughput, you don't want to save every packet that you sent in memory until you get an acknowledgement for it. Especially in those high throughput tests, generally you're only sending 1 or 2 frames. It's really, I sent a packet, it had a stream frame that maxed out the whole packet. This was the offset, this was the length. So you don't need a lot of memory to essentially track that. But you do need to keep track of it. So this is where we have this metadata, and the loss detection has this linked list of metadata. And this is what we're going to use on the ACK path to say, okay, here's all the packets we currently have outstanding. These are the ACKs that we got, and we're going to go through and we'll need to acknowledge them. So Robin asks, if I understood the frame building code, you construct the frames directly in the buffer. How do you then re-extract the metadata for, say, for the streams frame to store? So, yeah, so pretty much we construct the metadata and the frame itself at the same time. So specifically, let's look at streams. So here's where we write frames for a stream. It's got the same thing where it's got different flags. So for instance, like this is, we need to send a max data on a stream. We write the data, or we try to write the data into the packet buffer. If it succeeds, we then add that metadata to the packet builder's metadata. We add that flag to the metadata. So essentially, it's kind of this pattern of try write to the buffer. If writing to the buffer succeeds, add the flag to the metadata. And so the builder is keeping track of all this. This is kind of our helper, kind of like sandbox, junk place to throw all that while we're building. And at the end, you'll finalize this, and this builder takes everything, gives it as one struct to loss detection and say, here's the metadata for a packet I just sent. It's got all the information. So specifically for stream frames, I mean, obviously stream frames are special. They're different from every other frame because they're a lot more complicated. But this guy has all the logic to build those. Offhand, I don't even remember where we do the metadata. I think it's down there in the details. But suffice it to say, it's the metadata. It's a struct that's gonna have substructs for each frame, and the frame metadata will say what type of frame it was and any other details. This is this is, if you're interested, so this is our frame metadata. They have for each type of frame, these are the things that we need to keep track of. And we've got some other information. A lot of this has been kind of optimized to pack efficiently, because obviously you might have hundreds or thousands of these outstanding, and you want these to be as efficient as possible. And then this is at the packet layer. So you can see we have variable number of frames. We go into more complicated logic for allocating these. We have a pool allocator for each version of packet metadata for a different number of frames. So essentially, we've got a pool allocator for packet data with 1 frame, pool allocator for packet data with 2 frames, 3 frames, all the way up to our max, which is currently 12 frames. Again, like, we do a lot of work to never allocate, like really allocate data on the data path. And this is one thing that kind of really would lend itself to like needing to be allocated and freed quite often. So we do a little bit of extra work on top of the pool allocator to optimize this as much as possible. All right, so yeah, okay, I think I've answered all those questions. If anyone else has anything else, feel free to chime in. All right, so on the loss detection, one interesting side that people have asked about is how we process ACK frames efficiently. It seems like this ends up being a CPU hog for at least some implementations, or at least tricky to get right. So this is called in the receive path. We talked about that earlier, the QUIC packet receive path, but we didn't go into the details at the frame layer. This is just one of the frame calls that we have for processing that. I mentioned we've got this working space for decoded packets. So the first thing we do is we decode the wire format into our custom format that we have pre-allocated on the connection. This is our working space. This allows for dynamic, this can grow dynamically if necessary. If, say, for instance, we got a really big one, and it's capped as well, but generally we pre-allocate something like 8 ranges, and that works as long as you don't have a large number of kind of gaps or packet loss. So we decode that into our struct. Assuming it succeeds, we do some extra validation, do some ACK delay stuff, but then we process the ACK blocks. So this is the kind of the meat of loss detection, turning essentially ranges of packets that are acknowledged into a set of packet metadata that were lost or acknowledged. So we go through these. Again, when we decoded them, we reversed the order of the wire format. So this is an ordered list, essentially of numbers from smallest to largest. And then we're going to go through this list along with our, so this does some validation. We keep track of packets we think are lost for a particular amount of time, just in case they get acknowledged later. So this is going through that. We mark them as spuriously lost if they do end up getting acknowledged. But kind of the meat of this is we go through all the sent packets, and we then try to match those with the acknowledgements. And this allows you to essentially go through the lists in order. I know it looks like we've got a while loop and start inside of a while, so like a multiply, but you're actually going only until you hit the next one. So essentially this is just skipping ones that don't matter. So you can traverse each list once. You build up a list of which packets were lost, which packets were acknowledged. A lot of other loss detection stuff with keeping track of what's the largest acknowledged, path stuff, you have to do validation. And then assuming there were acknowledged packets, because it's theoretically possible to receive an ACK that doesn't acknowledge anything new, you then go and process all those packets. This is again an ordered list. We process them and do everything we need to do that. And with the newest, largest ACK, sorry, go back. There was, is it not here? Okay. Processing packet acknowledged also results in handling lost packets. So as you receive packets or acknowledgements for packets that are later than ones, either time or in count, you can result in lost packets, which will then trigger into congestion control. Data being acknowledged also triggered into congestion control, and you can update any timers that are necessary. So, but generally doing this model of first decoding into our working buffer and reversing the order, and then processing our ordered list of outstanding packets in parallel with the ordered list of packet ACKs allows us to go through everything in one pass very efficiently. And we're just going through metadata, and the metadata, just a linked list, allows you to easily add and remove stuff. Any questions there or any more details anyone would like? Okay. So the last thing I have, Dimitri?
Yeah, Nick, can I ask about the different piece of code in MsQuic?
Sure.
I was curious about the receiving of stream data. It seems that the receive buffer, the data is always copied into it. Have you considered optimizing for the common case, which is when no overlaps occur, and then when data can be read immediately? Because obviously, you decrypt data and then you copy it again, and then it's read. Have you tried or considered skipping the copying step?
So we have considered doing that, but the main reason we do what we're doing now actually goes back to batching. So in that model, what happens, or what would happen, would be every single QUIC packet you get would result in an up call to the application saying, here's a new packet size stream data, here's a new packet size stream data, here's a new packet size stream data. And there's a lot of back and forth between the app, where the model we have instead allows us to do copy it, process the whole receive batch, and then we flush it all at once. So there are some trade-offs there. Another complexity, at least with our implementation, is we have the ability for the app to return pending from a receive. So we say, here's a buffer. They can either return success, which means they drain the whole buffer. Okay, we're done with it. We can free it or do whatever we need, or they can return pending from us, and then they own the buffer until they complete it back to us. That pending model would not work out so great with giving them a pointer straight to the memory in the packet. It's doable, but you then have to have we have an application ref count on the packet. We can't free the packet until the application ref count goes to 0. There might be lots of stream frames in that one packet, and if they pended all of them, so there's a complexity part there, but there's also a batching part. But yeah, we've definitely talked about doing that, essentially allowing. What we've talked about is having like a flag or a mode that the app can set that says they want immediate delivery versus essentially the queued delivery. But really, it comes down to we want to batch as much as possible. So being able to give the application one batch, we view as worth the cost of the copy in most of the cases, because a lot of the times what happens is the app is then going to want to do something and copy all that, and then maybe kick its worker thread to process this. And if we have to do that for every single chunk, it ends up generating a lot more load at the higher layers. Essentially, it multiplies that. I can't definitively say one is more expensive than the other. I haven't tried them, especially in like a real production scenario. It's something we've thought about implementing. There are implementation complexities about doing that currently block us, and we haven't had a need yet. But it's definitely a valid way to do it. But we currently do not.
All right, thank you. That makes sense.
Sure. Robin asked, what if you indeed had spurious loss? The next act does include packet number you thought was lost. Do you wait a small time before actually retransmitting, for example, or is that just implicit in the packet batching or something? So it is possible that we mark something as lost and end up processing another packet with a separate ACK that acknowledges that loss before we ever retransmit it. So like imagine we receive a batch of 2 packets. The first one has some ACK ranges, the second one has some ACK ranges. The first ACK ranges mark packet 10 as we think it's lost because of, say, that we got an ACK 10 packets after it. But then the second one has an ACK for that packet, and we say, oh, it's no longer lost. In response to that first packet, we marked packet 10 as lost. Say it had stream data. We went to the stream and said, hey, this offset of data is lost. It needs to be retransmitted. We do some bookkeeping, update the stream state to say, okay, we need to send this data again. But then when we get the ACK for that in the second packet, we end up going to the stream and saying, hey, this data was acknowledged. And then it updates the bookkeeping again, and now everything looks nice and clean, and it says, okay, this is where we actually need to send next. Assuming nothing needs to be sent, there is some wastefulness in that the stream will be queued to send, but it won't actually have anything currently needing to send. If it did have stuff to send that was just later in the queue, that will be what's sent next. So bottom line, it is possible for us to not end up retransmitting that if we get that other ACK, but I don't know how often that would ever happen in reality. Does that answer your question, Robin? It's just an artifact of batching. Because you do batching, you batch work for the next layer. You receive all your packets, you batch everything that needs to be sent. Sometimes future things overwrite old things, or vice versa, or queue up more. It's just things that can happen like that. So the last thing I thought might be of interest and if anyone has any extra requests, feel free. But it's just kind of a high-level worker thread. So the worker thread is the driving force between all the QUIC protocol logic. And we have one of these per core. We use the term partition to essentially map a partition to a core, which corresponds with the RSS for that core. And each worker has a set of connections. Its main job is really just to say, okay, it's got a queue of connections that currently have a queue of work items, go through each connection, process its work items, go to the next one, process its work items. It also does other things, though. Specifically for a server, client not so much, but for a server, you have a couple kind of stateless operations that need to happen. Stateless in the sense that they don't correspond to a particular connection object. Sending retry packets, sending stateless resets, sending version negotiation packets, all of these we consider stateless operations because they don't correspond to a particular allocated connection object. So the worker is also responsible for flushing those. We've got, it's more of a DOS protection logic, but we've got logic for stateless operations in that we never have more than one queued for a particular endpoint at a time. In other words, if we receive a batch of in packets from a particular UDP4 tuple and say they were all, none of them correspond to a valid connection object, and we need to send a stateless reset back. The first packet in that batch that we process results in a stateless reset being queued. All the other ones result in nothing happening because they go and check the current queue that says, oh, look, that we already have a stateless operation queued up for this. No need to do anything else. So eventually, that queue is then drained by the worker, saying, okay, go ahead and do this. So what that means is we never queue up too much work than we can handle. So, or for instance, say we're really heavily loaded already, we'll queue up one item for each of that, but if it takes us a long time to drain that queue, then we're not going to be DOSed by having to send additional items because the first thing is still in that queue. So worker is responsible for draining that queue as well. And then the final responsibility of the worker is the timer wheel. So we have a custom timer wheel that drives all the timers for all the connections this worker owns. So this has a real nice effect of us needing absolutely zero abstractions at the platform layer for timers in general. We never call any timer, so nothing where we actually start a timer and say give us a call back or set an event or something when this timer expires. Everything is driven by our worker thread. So you can see it runs a connection, runs a stateless operation, and then checks the timer wheel. And if there are any timers to process, it processes the timers. Then it says, essentially, if we still have other work, or if we just did work, then we go back and keep processing the work. If we had no work left to do, essentially run the timer wheel. If we have no timers and no work, we essentially are just going to wait for the ready event. So it's a fairly straightforward model here, but again, this allows for the timer wheel itself to be partitioned. So this worker only processes the timers for connections in its partition. So again, it allows us to be really efficient with this. I'm trying to remember, there was, at least in memory usage, I remember there was a huge impact on Windows from going from using like platform timers to using the timer wheel. Is a huge difference. Efficiency-wise, I would expect the same, but I don't have like any real measurements or numbers to say for that. But bottom line, most of the work is just going to be happening right here. This guy's just sitting in this loop saying get next connection, process connection, get next connection, process connection, and this is what's driving all that work. And this does a bunch of stuff, and its main work is essentially this drain operations. It's got a queue of operations, essentially work items, that it just goes through the queue and does all the work. And essentially that's how really all of our workload is driven. Any questions on that? That's the end of what I had for a code walkthrough. It was quite a lot. No questions. The next stuff up is testing and tooling. All right. So testing, tools, analysis. So obviously beyond just having code, you need to try it out, run your performance tests, measure it, and see how things are working. Towards this end, I don't know, 6 to 9 months ago, I think I started this small effort to try to just write a simple standard protocol to test the QUIC layer. I've got a draft out here, and we implement this draft in our QUIC perf performance tool. The server side is pretty nice because you write one very simple protocol, and it allows you to test a bunch of different kind of scenarios, which we'll go over next. The client side, each side has to kind of be tailored for the scenario. But kind of a key thing here is we have this these tests. We wrote this tool, and we run these tests for every single PR, every single commit into master. So, for instance, where's my browser? Oh, somebody ran stuff today already. So you can see this is our Azure Devops pipeline for MsQuic, and batch CI is essentially when it runs on main, PRs for PRs. So for every single PR, here's an instance of a PR. Hopefully it's a good one. We run a number of jobs. You can see we've got quite a lot of jobs that we run and do a lot of different building, testing, interop testing. But the thing I want to focus on here is we have performance tests that are run on a couple of the platforms currently. You see Linux here, but this is only running on a VM. So we only have Windows hardware set up in our lab for doing this, but we run these tests for every single PR. And we've got some thresholds, so you can see, like for this, we ran a particular upload test using OpenSSL x64 on Windows, and the average was down 1.81%. This is within our threshold, our acceptable threshold for the test, so the job still passed. So we run a number of different jobs for a number of different test cases. You'll notice some of these still go down quite a bit, and we still mark them as success. We still have quite a large variability in some of our test cases. We haven't been able to really make those things super efficient. RPS especially is hard to get really consistent on where you're creating hundreds or thousands of connections, and you're dealing with numbers of like 1 million requests per second. You can get a lot of variability. And for this, you can see 89, almost 900,000, 776, 902. So there's a lot of variability in here, which makes it a little hard to have small acceptable metrics. But bottom line, we run all these tests for every single PR, every single commit, to give us an idea of how things are doing. Let's see if I can find one that failed. This is going to fail. Yeah. So Lucas asked, how stable is the CI environment with respect to consistent performance testing? Pretty stable. So since we have 2 pairs of dedicated machines. I've got the specs listed here. So essentially, we've got 2 pairs of machines with these specs, and they're pretty beefy server-grade machines that all they do is sit around and wait for our jobs to be pushed to them. We periodically update them to the latest Windows Insider builds that we use for testing, but they're just sitting there pretty stable. So they're connected. They've got, is it 50 gig NICs or 40 gig NICs? They've each got 50.
50.
Yeah, 50 gig NICs connected with a 50 gig switch. So they're pretty stable. Does that answer your question, Lucas? Yeah, so the machines themselves are pretty stable. As you can see from some of the results, I'll go over this a little bit more. Some of the results aren't quite as stable as we'd like. And you can see single connection throughput generally fairly stable. Handshakes per second fairly stable. RPS is all over the place, and we haven't gotten quite to the level of stability that I'd like for that. So when you do happen to have a failure, so you can see OpenSSL had a job that failed here apparently. So you'll see something. Oh look, our throughput, our threshold is 8%, but it went down by 10% for this particular scenario. And we could go back and look at this, but usually if it's close enough, and especially on OpenSSL ones, we tend to ignore a little bit more. Ideally, we'd investigate all these and try to figure out why, but most of this comes down to there's just still enough variability in the setups, in the systems, in the tests, that we ignore these type of failures, unless it's something like, oh, it dropped by 50%. And this particular one, you'll notice, was actually run on main. So this is, main is obviously going to be after you did your PR. So we'd look at these more on PRs than on mainline commit. So mainline commit is mostly about generating the data that feeds into this dashboard. But we have that ability to see what failed. We can adjust those thresholds as necessary. If we see a large number of failures, larger than we'd like, okay, look, it looks like maybe we're just wrong, or maybe the variability went up for some reason. Yeah, it's all easily changed and modified. So I said we run that for every PR, and this really allows us to catch any major regressions before the code is even merged. And again, just high level, some of the scenarios that we test right now, and there are other ones that we might expand to in the future, but like single connection throughput, requests per second, for that you really measure what is the maximum request per second you can hit, but also important, what are the latency numbers for each response time for those requests. Both are important. And then another one that I like to measure is just handshakes per second, which really comes down to how fast is your TLS stack, because that's where all the CPU usage is found. But you can find some interesting bugs and synchronization issues when all you're trying to do is handshakes as fast as possible. Again, we've got this dashboard. It's public. It's not great in the terms, or in the sense of our HTML coding abilities are quite subpar to at least some people. We write kernel code, not HTML, so if you play around with the site, formatting can get really weird if you view, say on a phone. It really sucks to look at on a phone, but anyone wants to propose a change, all the code is public on our GitHub as well. Feel free. Then on the tooling side, obviously being able to measure these is one thing, but as you encounter issues or as you want to try to improve the current state of things, you need tools to help you in this process. We have a number of events that we use to instrument the code. We use a binary logging format for both Windows and Linux. We make use of a tool called Clog, which is another Microsoft open source project that allows you to dynamically generate these events fairly easily just from code you write, and it will put it in the correct format. And then we use Windows Performance Analyzer to analyze. Currently, we only support the Windows events, but it's just something we haven't done yet to implement support for the LTTNG events on Linux. WPA natively supports things like the CPU flame graphs, and we wrote a custom extension for supporting our own events to generate QUIC specific traces and stuff. And one thing I'd like to do also is support QLog with our plugins. Let's see. So first, I'll just go through some pictures and then have a quick demo to show how you can actually interact with this stuff. So this is just a flame graph of a Windows user mode sender, sending data as fast as possible. I only have symbols loaded for MsQuic code. So you can see the biggest thing here, right here, is the platform encryption code. So this, I believe when I looked at it, was for this particular trace, 58% of all CPU usage was spent in the encryption of packet payload. This is the UDP SYN code path. Up here you can see TCP/IP. So, and this is not more than 15% of all CPU usage is spent in the UDP SYN path. Over here is UDP Receive. Again, I don't expect you to be able to easily understand that from this, but just from experience, since you can see we have two different threads running here. This thread is the QUIC worker thread. This thread is the data path receive thread. And receive being so small makes sense because all this is doing is receiving ACKs. So this just shows you how much UDP layer and some QUIC validation layer is spent on that. And then this is what we pretty much are, at least for this implementation, building up stream frames. And I think this is having to do with the receive path. But I'll get into details a little bit better when we follow through with these, or when I give you the walkthrough of WPA. And this is an example of one of the, or a couple of the charts we can generate with our plugin. So this is what we wrote to generate. This is an instantaneous data rate. For this particular test, it was just under 3 gigabit speeds. This is RTT in milliseconds. So you can see RTT was, I don't know, 5 or 6 milliseconds on average, but you can see it spiking sometimes pretty high. Some of the kind of in-flight congestion window variables of note, like CWINs, and then how many bytes are in flight, what's the stream flow control, what's the connection flow control. And this one is one that I like quite a lot. It's not particularly useful for this one, but usually whenever someone comes and says, hey, my performance is not great, it's not what it should be, and that's a lot of times very subjective, and you're like, okay, why? So really what you want to do is, what is limiting your throughput? So this chart explicitly lists out, for a given time, what is blocking the TX state? Like, what are the reasons we aren't sending at this particular moment? Whether pacing is currently saying we shouldn't send right now, or congestion control, flow control, where the app hasn't queued up enough data. This chart is extremely useful for those kind of diagnostics. So right now I have one graph or one file open. Let's see. So see how fast it's. The one thing is I'm again going back to us using binary. So this is like a 1.8 gigabyte file that I have opened right now. So it does take a little bit of time to process these, but like let's say I'll open, I think this is that same file I took the picture from. So I'm just going to open up a couple of these graphs. So you'll see that this one had a test with 5 different connections on it at any time. So we ran the same test 5 times. This is the throughput. We can grab any particular one. So let's say I want to look at this connection. Zoom to that. Make these a little bigger. You can say, okay, throughput was pretty consistent for this. RTT kind of all over the place, maybe an average of about 7 milliseconds, but jumping as high as 15 or 19 milliseconds. And like, okay, like we might notice, hey, look, this is interesting. It went from really low kind of variance in the instantaneous throughput to a little bit bigger, and I also noticed all this stuff. So I can go and say, let's zoom into that. I can expand this. So how I have this set up is this top level stuff is connection wide, these are stream wide. So you can see it looks like we still have some work to do on our pacing logic. Again, how it interacts with these high throughput tests is a little bit complicated, but for some reason we started pacing a little bit more in this time. And you can see that is the reason why we have these drops in instantaneous throughput. But the pacing logic was kicking in for some reason. Though right here, we can say, hey, look, the app was blocking throughput for a little bit of time. So zoom in more, and you can see like how long this happened. So start in. So the duration of this, the app was blocking throughput for, what's that, 1 millisecond. So these are the kind of things it says, I'm like, ideally, since this is a performance test, we should have it set up so that the app never blocks throughput. We want to get things, but this allows you to really drill into the details of these things. We have a lot more graphs and tables, but some of these are more interesting in network limited tests where you really have congestion control really kicking in, or maybe you're playing around with different congestion control parameters or playing around with pacing logic. This allows you to drill in and see like how exactly did the system perform, and you get all these details. Really helps diagnosing things. I'm just going back to the chat now. Are there any outstanding questions? I see Thad was responding for some of these things. Yeah, I see Robin. Yeah, we have events that explicitly trigger this. Like for this blocked state, we have the connections themselves and the streams keep track of what is currently blocking, and it's a bit field. You can have multiple things blocking you at the same time, theoretically. And we log, anytime those flags change, we log that. And I found that extremely useful in diagnosing things, to be able to say, hey, look, the connection is currently blocked because connection flow control, and stream 6 is blocked because the app hasn't queued any data, and stream 8 is blocked because the peer's flow control for that stream isn't available. So having that information and logging an event anytime it changes allows you to generate this type of graph, and it is really useful. All right, so we've got 15 minutes left. I could spend more time on this, but I just want to kind of jump to the conclusion and then have a little time for questions. We've targeted a performant design from the very beginning. We knew we were going to want to get both SMB and HTTP, and particularly for SMB, bulk throughput is like their number 1, number 2, number 3 goal, and they want performance. So we needed to have a design that if we were ever to get them, like convince them to use QUIC, we needed to be as performant as possible. So really from the get-go, we've always had that in mind, only behind functional support. Obviously, it needs to be functional, it needs to interop, but our number 2 goal has been performance. So beyond that, though, just having that as a goal and having that in the design architecture is one thing, but we constantly test this and have these automated tests to improve and to prevent any regressions as we're going. And we've spent a lot of time on custom tooling and logging to drive the improvement even more. So it is definitely one of the primary things we spend time on in our implementation. And CPU performance is just one thing. WAN performance, or essentially performance in a network limited scenario, is another thing. You probably saw we have automated tests for that, which we use kind of simulated environments. And that's an area that's still under a lot of active development as well. So after that, I open it up to anyone else who has any questions or would like to see anything else.
I have a question regarding ACK performance, Nick.
Go ahead.
Do you plan to implement the delayed ACKs extension? Because obviously receiving and sending as few ACKs as possible will increase performance. Thank you.
Yes. Yeah, I have got an issue of tracking it. It's on the to-do list to at least handle it on the receiver side. I'm not sure what we're going to do on the sender side of that, but yes, it's definitely on the to-do list.
Hello.
Hello?
Thank you for the talk. I tested the single connection throughput this morning and I found something quite interesting. The throughput grows very linearly and stably with as the bigger size of the delivery block until 30 gigabytes. I'm wondering if there's any optimization for the big file size, or is that a slow start problem?
So how our APIs designed from the application perspective is we have, I didn't go into a lot of details because we only have so much time, but on the application side, when you're sending, we have 2 models for sending. We have buffered and non-buffered sending. So both ways provide a mechanism to essentially tell the app that you need to have at least this much data queued up to ensure that you're not the limiting factor. So again, going back to that chart I was showing, saying what is currently blocking throughput. If the app wants to achieve highest performance, it never wants to limit throughput itself. It needs to make sure there's always enough data queued up and buffered for QUIC to run as needed. Assuming the app has enough queued, then yeah, it comes down to at the beginning of a connection, either congestion control or sometimes flow control are usually the limiting factors in the first couple round trips. But once you reach that limit, then you usually don't have a problem. Like, let's just take this first guy. This one, this is before the handshake, so it's not particularly relevant. So you can see right here we have build up. Throughput is starting to increase, and we have a number of things that end up blocking throughput at the beginning. So obviously, before the handshake, this is not a zero RTT connection, so stream flow control, you're not allowed to create any streams at the beginning. But eventually the handshake proceeds far enough and you're allowed to. But then pacing kicks in, because at the very first we had a lot higher RTT because it ends up getting inflated because the handshake itself takes so long to execute. Well, relatively long, 11 milliseconds or 12 milliseconds. And that inflates RTT at the beginning. Eventually, as that goes down, pacing logic adapts to that, and then congestion control is kicking in a few times. There was a time where the app was blocking. So there are a number of things that can block, but once you kind of hit that steady state, that's when essentially everything should go clear and you shouldn't be blocking. But going back to, it should be independent of what the app is queuing as long as the app is queuing enough. Does that answer your question?
Yes, thank you very much.
Any other questions? All right, well, if that's the end of the questions, thanks a lot for everyone joining me. If you have more questions later, feel free to post them on Slack or a discussion on GitHub or an issue. Like I said, we're really motivated on the performance side of things, so we're happy to work with anyone who would have more comments or questions. And with that, I think I'll go ahead and end it. I will try to get it shared out. It was recorded. I need to figure out how to share it externally. But thanks again for everyone joining.